next speaker, can you please share your slides? Our next speaker is Mario Giuseppe Guarcello, who's going to talk to us
Close
about
enough.
going to talk to us about simultaneous optical and X-ray variability in young stellar objects from the CS12264 project. And Mario's coming to us from Palermo at INEF.
Okay. Oh, thank you very much. Thanks for giving me this opportunity. Do you hear me? And do you see the pointer moving?
Yes.
Okay, perfect. So what I want to do today is to show you the capability of the studies in the time domain, combining optical and X-ray data to study the properties of the young stellar objects. And what I want to do is to show you this by using the results taken in the framework of the CSI2264 project, which was a project focused on the young cluster NGC2264, which is less than 4 million years old. It's very rich of prime sequence stars. And I will focus on the results obtained from a Chandra observation, 300 kiloseconds long, divided in 4 different epochs, and taken simultaneously to the Corot observations. Corot was this wonderful satellite that was designed for the search of exoplanet and was performing optical light curves with a cadence of 50 and 300 seconds, so with a wonderful cadence. And in particular, we have 374 prime sequence stars in this cluster for which both X-ray and optical data are available. So first, why we're interested in this science? The prime sequence stars, mainly when they are very young, younger than 5 million of years, they are typically surrounded by a protoplanetary disk, which is a disk of dust and gas orbiting around the star, and that may evolve in a planetary system. Now, the very inner region of this disk are actually quite crucial for several reasons. For instance, for the magnetic coupling between the star and the disk, the accretion of gas from the disk onto the star, and also for the evolution. It plays an important role for the evolution of the angular momentum of the entire system. The problem is that this region is very narrow. I'm talking about a few 0.1 astronomical units. For instance, if you take a look at this image of a protoplanetary disk around the star HL Tau taken by ALMA, the extent of this disk is about, the radius is about 200 astronomical units. So this region is a very narrow spot inside the disk. So it's very difficult to actually directly study and probe this region. I want to show you that with studies in the time domain, we can actually do it. So first, prime sequence stars are variable sources. And this was one of the properties of the prime sequence stars considered by Joy in the 1945 to define this new class of object called the T Tauri stars, which are prime sequence stars with disk. I mean, it is evident if you just look at this optical light curve, these are very old light curves of 2 T Tauri stars. And for instance, you see there is a variability of almost 2 magnitudes here. Now, this variability is due to several phenomena. Among these phenomena, the 3 main phenomena I'm going to show you now. The first one is rotation and magnetic activity. This, of course, is not a prime sequence star. This is the sun, quite old. And these are images taken by the SDO. Now, if you take a look at the photosphere, during the rotation of the sun, you see the appearance of a magnetic active region in the photosphere, which contains spot. Simultaneously at the same location but at different age, you see the corona. There is the appearance of a X-ray bright active region in the corona. So if we were looking not at the sun, if we were looking at to a distant star, so we are not able to resolve the details of the star, we could see a decline of the optical emission because of the appearance of the spot, and an increase of the X-ray emission because of the appearance of the active region in the corona. So these magnetic activities can affect the variability of the stars, and the prime sequence stars are very active from the magnetic point of view, thousands of times more active than the sun. The second phenomenon is variable extinction. In this case, for instance, in this case, we have a disk rotating and around the star, and the inner disk is not flat. It has structures, these homogeneities, that can obscure the star during the rotation of the system. Of course, when one of these structures come in front of us along the line of sight, we have an increase of the optical extinction and an increase of the X-ray absorption that, as I will show you, can help us probing the properties of the material. And we also have accretion, as I said before, accretion of gas from the disk onto the star. This accretion can be completely unsteady, like the accretion shown in these simulations made by Colombo and collaborators. This is the disk, this is the star, and these are accretion funnels of gas that turn on and turn off after a while. So the emission of this process, which is an emission in optical, mainly in the most energetic part of the optical band, UV and soft X-rays, is intrinsical variable and can also be modulated by the rotation of the star. So again, this is an intrinsical variable and multi-wavelet phenomenon. So now let me show you what we have done to 2264. We've been able to use the optical light curves of the stars in this cluster to actually isolate those time intervals in which there was something important going on. For instance, take a look. This is a nice light curve in black taken by Corot of one of the stars in 2264. This light curve is not flat, it's not sinusoidal, is a mess dominated by by spikes, which are accretion bursts, like for instance this one, or dips, like this one, which are due to an increase of the optical extinction. So we define the time intervals isolating this phenomena. We extracted the X-ray photons during these time intervals, and we performed what we call a time-resolved X-ray spectral analysis, fitting the X-ray spectra to 1 temperature, 2 temperature thermal plasma models, all in those time intervals. So now let me show you the results, some of the results. For instance, let's consider a star with optical dips. So this is the light curve of one of the stars in 2264 with the optical dip. There is a large dip here and 3 narrow dips, which are due to an increase of the optical extinction due to the circumstellar material. We have done this calculation, and in this case, we were looking for variations of the X-ray absorption, the NH, which is 0 during all the time intervals with 2 exceptions. And in particular, in both cases, we have in these 2 intervals 2 optical dips. And in this case, as you can see here, the increase of the NH is also significant. So we have here a very nice evidence for a simultaneous increase of the optical extinction and the X-ray absorption, and also an evidence for the capability of the circumstellar material actually absorbing the X-ray photons, which is something useful for several theories, like for instance, the photoevaporation of the disks. But we can do even more because, for instance, in 6 dips, we've been able to calculate some of the quantities of the dips. NH, AV, the full width of maximum, the rotation period of the star. And so we calculated some of these ratios. For instance, you can see the plots here, NH over AV and the ratio between the full width of maximum, the rotation period of the stars. And the values that we found using the results taken by the project are typical of intervening material, which is gas-rich and confined in very narrow structures. So something you expect from accretion streams, which are likely due the cause of this simultaneous increase of optical extinction and X-ray absorption. So talking about accretion, this is one of the light curves of one of the stars in which is dominated by accretion bursts. You see that all these spikes in the light curve. There's a very big accretion burst here. We repeated the calculation. This time we fitted the X-ray spectra with thermal plasma models, and there is no way to fit during this burst, for instance, to fit the X-ray spectrum with a 1 temperature model, thermal plasma model. You need 2 temperatures because of this excess of soft X-ray emission here. So we have some evidence for the fact that during the optical burst, we can detect this soft X-ray emission, which is quite important because, as I said before, the soft X-ray emission is connected to the accretion process, but has always been very difficult to actually distinguish, to actually resolve this soft X-ray emission because people didn't have these light curves to isolate the burst, and it was difficult to distinguish it from the coronal emission from the star. And it can be useful to probe the accretion process. We can do even more. we have taken all the time intervals we have defined, and these time intervals we have fitted the X-ray spectra with a two-temperature thermal plasma model. We have calculated the ratio of between the normalizations of the soft and the hard component, and you see that there is a bunch of time intervals in which there is an evidence of a significant soft X-ray emission. And most of these time intervals, the black dots, are actually time intervals in which we observed optical burst. So again, we have with this very good evidence for this presence of soft X-ray emission during accretion that, as I said before, can be used as a diagnostic for the properties of the accretion process. So in the last minutes, let me show you what we have done for the stars without disk. We have repeated the approach, but this time what we have done was to sample the optical flux and the X-ray flux. So the optical, in this case, we have a light curve. This is the optical flux. This is the X-ray flux. In order to search for the correlation between the optical and the X-ray variability. And in this way, we sorted the stars without disk in three groups: those with a correlated variability, anti-correlated, and non-correlated. These are a few examples. For instance, in each of these plots, you have the X-ray flux and the optical flux. In this case, there is anti-correlation. In this case, there is correlation. But I want to go a bit fast here. Now, the anti-correlated variability can be understood if we remember the rotating sun as the simultaneous appearance along the line of sight of a dark spot in the photosphere causing a decline of the optical light curve, and bright spot in the corona causing an increase of the X-ray emission.
2 minutes.
Thank you. By the way, we also can connect this variability with the properties of the stars. For instance, the rotation of the star. This is a plot in which you see the rotation period of the stars and the three correlation classes: anti-correlated, non-correlated, and correlated. And there is a clear difference. If you see here, for instance, all the anti-correlated sources but one rotate slower than the correlated sources but one. This is a very nice evidence for the fact that rotation plays an important role on the correlated variability between optical and X-rays. We played a bit with the literature. We have used the results by other people to actually build a scenario in which the stars which rotate slower, the primitive stars which rotate slower, typically have a more ordered magnetic field. And this results in a population of a small number of spots, but larger. So something that you expect from spot-dominated sources. So in this speculation, because this is a speculation, anti-correlated sources are spot-dominated sources. Of course, there are projects like, for instance, MATIS, in which the correlation between the topology of the magnetic field and the properties of the stars will be studied in great details. In this picture, then, it's obvious that the faculae dominated sources are likely, the correlated sources are likely faculae dominated. In this case, the effect of the dimming of the optical emission due to the presence of the spot is overwhelmed by the presence of the network of faculae, which cause an increase of the optical emission. Something that we know actually occurs in the sun when the sun is in this maximum of its activity cycle. And the network of faculae cause an increase of the total irradiance of the sun. So I ran out of time. So I just want to leave you with a conclusion. I hope that I convince you that studies in the time domain, combining, so in the multi-wavelength regime, combining optical, X-ray, and other wavelength, is very powerful to probe properties of the young stellar objects that otherwise are quite difficult to study.
Thank you, Mario, for an excellent talk. Please enter your questions into the Q&A box. We have a question from Rafael Martinez Galarza. When a pre-main sequence star flares in X-rays due to a magnetic event, what is the range of X-ray variability that you expect? By how much does the Chandra broadband flux typically increase? And what is the maximum variability measured so far?
That's a tough question. No, we have, there is a nice paper on this project that has studied flares in this project. So in the stars in 2264, and there is a wide range of possibilities. So you go from very narrow flares to super flares, in which there is an increase by order of magnitudes of both the optical and the X-ray variability. So there is a very huge range in which these quantities vary. But it is also nice here to perform these studies in the multi-wavelet regime, because in this way you can probe both the properties of the hot plasma filling the coronal loop and the material in the photosphere, which is heated by the whole flaring process. So in this way, by combining optical and X-rays, you are probing both what is going on in the upper atmosphere in the corona of the sun and what is going on in the photosphere. So it's an excellent tool actually to probe all the interplay between different phenomena during flares. It's something that we have done, for instance, in the Pleiades, and is another excellent field for the for a multi-wavelet approach in X-rays and optical and infrared and so on.
Great. Thank you, Mario. I think that's all the time we have for questions. Will the next speaker please prepare their slides?